Welcome back to Historic America AI. In today's video, we're diving into one of the most revolutionary fields of science, the history of quantum mechanics. Quantum mechanics has dramatically transformed our understanding of nature at its most fundamental level, specifically at the scale of atoms and subatomic particles. Over the next few minutes, we'll walk through the fascinating history of how quantum mechanics evolved. To start, let's go back to the late 19th century. Back then, classical physics was dominated by the ideas of Isaac Newton and James Clerk Maxwell. Newton's laws of motion and Maxwell's electromagnetic theory explained much of the physical world. But as scientists started investigating things at smaller scales, new problems emerged. One of these problems was blackbody radiation. Classical physics predicted that as the radiation wavelength decreased, the intensity should increase indefinitely. But experiments showed otherwise. This mismatch became known as the ultraviolet catastrophe. In 1900, a German physicist named Max Planck offered a solution. He proposed that energy is not emitted or absorbed continuously, but rather in small discrete packets he called quanta. This was a groundbreaking idea. Planck's equation E equals hf, where h is Planck's constant, set the foundation for what would become quantum mechanics. Next, in 1905, Albert Einstein expanded on Planck's work when he explained the photoelectric effect. Scientists noticed that when light hit a metal surface, it ejected electrons, but only above a certain frequency. Einstein proposed that light itself is made of energy packets, which he called photons. His work earned him the Nobel Prize in Physics and cemented the idea that energy and light are quantized. In 1913, Danish physicist Niels Bohr applied quantum principles to the structure of the atom. Building on earlier work, Bohr suggested that electrons orbit the nucleus in specific, discrete orbits. These electrons could only jump between orbits by absorbing or emitting energy in quantized amounts. His model successfully explained the spectral lines of hydrogen, something classical physics couldn't do. Moving forward to 1924, French physicist Louis de Broglie proposed that particles, like electrons, might behave like waves. This idea of wave-particle duality was later confirmed in experiments and became a core concept in quantum mechanics. Another major development came in 1927 with Werner Heisenberg's uncertainty principle. Heisenberg showed that you can't precisely measure both the position and momentum of a particle at the same time. The more accurately you know one, the less accurately you can know the other. This principle revealed a fundamental limit in our ability to predict nature, shaking the classical idea of a deterministic universe. Then in 1926, Erwin Schrödinger introduced wave mechanics. His famous equation describes how the wave function of a quantum system evolves. This wave function represents the probability of finding a particle in a certain state. Schrödinger's equation became one of the key pillars of quantum mechanics. Max Born added to Schrödinger's work by suggesting that the wave function didn't describe a physical wave, but rather a probability distribution. This introduced an element of randomness into the heart of physics, where previously everything seemed deterministic. In 1928, British physicist Paul Dirac combined quantum mechanics with Einstein's theory of special relativity. This led to quantum field theory, predicting the existence of antimatter, which was later confirmed experimentally. Dirac's work paved the way for future developments in quantum electrodynamics and the standard model of particle physics. Quantum mechanics didn't just revolutionize physics, it also raised deep philosophical questions. The Copenhagen Interpretation, developed by Niels Bohr and Heisenberg, suggests that quantum systems don't have definite properties until measured. This interpretation challenged our classical notions of reality, leading to famous debates, such as Einstein's remark that God does not play dice with the universe. To conclude, quantum mechanics has completely changed our understanding of the universe at the smallest scales. From the initial struggles of classical physics to the introduction of quantized energy by Planck, and the development of key principles by Einstein, Bohr, Schrödinger, and others, quantum mechanics remains one of the most exciting areas of science today. Thank you for watching. If you enjoyed this video and want to learn more about the history of science and physics, don't forget to like, subscribe, and hit the notification bell for more content. See you in the next one.